Free radicals. My exploration into free radicals has taken me in unexpected directions, but that may be for the best. Let's start at the beginning. The protons are in the middle and the electrons go around the outside. The electrons are in energy levels. There's 2 plus 8 plus 8. The energy levels have to be either full or empty. This is the octet rule. During a chemical reaction, the reactants meet the octet rule and the products meet the octet rule. This is not the octet guidelines. This is the octet rule. But to go from the reactants stable under one energy configuration to the products stable under a different energy consideration, something has to give, and this is where the free radical comes in. The free radical is a violation of the octet rule. They tell us that the life expectancy of a free radical is about a billionth of a second. So there's the octet rule, and the exception is a particle that has a half-life of a billionth of a second. That's a billionth with a B. For an example, let's use diatomic chlorine and methane gas. If you heat up chlorine gas and methane hotter and hotter, the first thing that happens is that the diatomic chlorine breaks into two chlorine molecules. It breaks into two chlorine atoms. These are atoms as they are found on the periodic table, 7 electrons in the outside orbital. These chlorine atoms are free radicals, and they have a half-life of a billionth of a second. The chlorine free radical reacts with the first thing it comes to, which is going to be the aliphatic hydrogen on a methane. It takes that hydrogen, jerks it clean off, proton and electron both, and the chlorine becomes stabilized as hydrogen chloride gas. There's a scar left on the methane. The methane becomes a free radical also, and then it has the option of reacting with a different chlorine free radical to form chloromethane. Let's look at a reaction diagram. The y-axis is the energy axis. The x-axis is, they call it the reaction coordinate. The products are on the right. The reactants are on the left. This distance is the energy of activation. So this is the heat that goes into the system to form the chlorine free radical. The chlorine free radical is like a bicycle driving on the top of a fence. Let's look at a metabolic reaction. The physical science, the physical chemistry is exactly the same. But biological reactions are always enzymatically driven. Recall that the enzyme is a catalyst, and the catalyst lowers the energy of activation. So everything is exactly the same. There's products and there's reactants. There's free radicals at the top of the energy curve. But this energy of activation goes from something big to something that really doesn't amount to very much. Metabolic reactions are always in the friendly environment of a cell. So there's no radical drop-off on either side. The free radical is now a bicycle riding on a sidewalk. It's probably a narrow sidewalk, but it's a much gentler situation. The free radical still has a half-life of a billionth of a second. Free radicals leak out. The system is not perfect. Reactions involving oxygen are especially problematic. This includes photosynthesis and aerobic respiration. Metabolism leaks free radicals, and they cause all sorts of problems. And this goes back to the very infancy of life. And life has come up with systems for dealing with the free radicals. These are the antioxidant systems. So since the beginning of life, cellular biology has been about free radicals, and then this antioxidant business, which is in there to take care of the free radicals. But evolution being what it is, free radicals have been put to all sorts of uses. And now all organisms, especially mammals, us, our cells and our blood are a delicate balance between free radicals and antioxidants. So why have I become so obsessed with free radicals? And why am I so concerned about this particular video? Even with all the progress in genetics and molecular biology and biochemistry in general, the whole thing seems almost completely beyond comprehension. But the fact that free radicals are a mistake, free radicals, it's like this should have gone back to committee. This should have gone back through R&D. Something should have been done to prevent this from happening. The very existence of free radicals as a mistake in metabolism brings the whole thing into a realm of possible understanding. I think the existence of free radicals is sort of an invitation in genetics that this is something that we can figure out and this is something that we can understand.